Okay, today, first hour, I'll give a very short review of vectors, then I'll complete parametric space curves, and then we'll have a quiz about these. And next hour, we'll start with the new subject. Okay, so for vectors, so let's say remarks on vectors. So let me start with three vectors. And C. Okay, so our first definition was the dot product of these things. So we wrote this. The whole nice thing about these things is that it has a both geometric and algebraic interpretation, and the algebraic version can be easily calculated. So that makes this useful. Okay, and what we are in most cases interested in finding this number is that this number is equal to the length of A times the length of B times cosine theta, where theta is the smaller angle between A and B. Okay. So this part, on the other hand, okay, let me write it with a different color to emphasize what we are doing. So this part, for example, B, is the length of the projection of B, of the vector B on A. Okay, so this also we use this to check if these vectors are orthogonal or not. Okay, so A dot B is equal to 0 if and only if A is perpendicular to B. Okay, so that was what we remember from dot product. And then we have, okay, let me start with B cross C. Then we have B cross C. Okay, so again we have a way of calculating B cross C using only the components. So that was the determinant of, okay, let me use this notation for determinant. So let me emphasize that I, J, K are the normal unit vectors. Okay, so then this is the determinant B1, B2, B3, C1, C2, C3. Okay. And this is a vector. This vector is perpendicular. Let me use now the common word. Perpendicular to both B and C. Okay. And again, we have something about its length. Its length is B cross C is length of B times length of C times sine theta, where theta is the same theta. So this time, this is, if you write this as B, if you write this as C, then we obtain a parallelogram here. So it is this area. Okay, so this number is B cross C is this shaded area, is the area of this parallelogram. Okay. And now let's do one more thing. This is a vector. Okay, I dot product it with A dot product B cross C. Okay, so this is a vector perpendicular to here. So this is B cross C orthogonal to both B and C. Okay. First of all, I know how to calculate this because I take the dot product of this. It will be here. A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay, so it's easy to calculate it using only the coordinates. So what happens is, now let me draw this picture now. Okay, we have a parallelogram like this. So this part is, so let me do this with these colors so that, okay, so this one is B. So this vector here is C, and this vector is A. Okay, so when you take the cross product of, B and C, okay, so you obtain this perpendicular vector B cross C. Okay, now taking dot product of A with that, we get the length of the projection. So when you take this part, okay, so this part is the height. Okay, so now this is projection of A. So this is A cosine theta. Okay, so if this angle is theta, okay, let's give it a different name, alpha. Okay, so this is length of A times length of B cross C times cosine alpha. Okay, so that's height. So this number is equal to the volume of this parallelepiped, because height of this length of B cross C was the area here, and I'm multiplying with height. Okay, so this is then equal to so A, well, this has to be in absolute value. Okay, so this A dot B cross C, okay, in absolute value is the area of the parallelepiped formed by these vectors. Okay, so these are the geometric interpretation. Again, I repeat, the nice thing about these things is, given these vectors, we immediately calculate these using the coordinates of this. Okay, so you don't have to worry about cosines and lengths and other things, but the values are interpreted like this. So now we can make use of this to check if three vectors are in the same plane or if they are collinear. When they are collinear, we have better ways. If they are not collinear, using this, we can immediately check that they are not collinear. Okay, so let me mention that now. Okay, so R A, or instead of asking the question, let us give the answer. Okay, so this is what we are interested. A, B, and C are in the same plane. So we call it coplanar. If and only if, so both things are the same. Okay, so we make this interpretation. B and C are of course, B and C form a plane. A is in that plane. Using this notation, the parallelepiped they form has zero volume. Okay, so if A must go up away from this plane so that there will be a volume. Okay, if it is in the same plane, there is no volume. Okay, so then this says that if I take A1, A2, A3, B1, B2, B3, C1, C2, C3, this is equal to 0. Okay? No volume of the parallel pipette, so no parallel pipette. So 0 volume. Okay. Are they collinear? Are the points? Now I look at these as points. B, C, R along the same line. Along the same line. So we call this collinear. But now we have implication only in this form, but we will use it backwards to get some result. If they are along the same line, then they are along the same plane. They are in the same plane. They are in the same plane. Okay, but when they are in the same plane, we know that this determinant, the above determinant, the determinant is equal to 0. Okay? So, since when we know that the determinant is 0, we follow these arrows, we are stuck here. This doesn't imply that they are along the same line. But if the determinant is different than 0, then we know that they are not collinear. So that's an easy way to check that they are not along the same line. We use this as follows. If this determinant is different than 0, then they are not collinear. Okay. If the determinant is equal to 0, then you have to go back and check. With 3 dimensions, 3 vectors, it's easy. Okay, so A, B, C are collinear if and only if. So there is a number lambda such that choose one of them, say B minus A is equal to lambda times C minus A. If the numbers are small, then this one is easier to check. But if the numbers look complicated and you don't want to go into this, such a determinant is always easier to calculate. But if the determinant is 0, then you have to go back and check if you can find such a lambda. Okay, so this is one part of the review of vectors. Then we have lines and okay, so maybe lines and let me do it over here. Okay, a line is given by a point on it, point P. Okay, we use vectors on it, and a vector N parallel to it. Then the vector equation is you first go to the point P, then you follow the direction of the parallel. T is in R. Okay, so this is the first thing you write about the line. Then, okay, parametric equations, you write x equals the first component, y equals the second component, etc. And then symmetric equations, from the parametric equations, you eliminate t. Okay, so the other parts are just algebraic manipulations, but this is the main idea of writing a description of a line. A plane in R3, okay, so we are going to work in R2 or R3. R2 is the same, you just keep the last coordinate 0. This is also in true. The general description is also true in Rn. So maybe let me just say a plane is given by a point P on it and a vector N perpendicular to it. Okay, so for both of them we need a vector, but in one of them, if we know that the vector is parallel to the line, then we are done. In the other one, an easy way is to find a vector which is perpendicular to it. Then the equation for this plane is n dot x, y, z. Okay, if you are in n space, then here you put n components, and unknown components is equal to n dot p. Okay, so the dot product of every point in the plane with the normal is the same. Okay, so that's how we express this. Okay, so I think these are the things that I wanted to review. Yeah, okay, so that's all. Okay, now let's finish this arc length of parametric curves process. Okay, so we'll look at arc lengths of parametric curves. Okay, so I think I want to start with, so here I wrote something else, but let me first start with parametrization. Okay. So we have a curve. Okay, so we have such a curve in space. Parametrizing it by something is you look at the real line and you take an interval a, b, and we have a parametrization like this, say rt. Okay, so this is a vector rt. So r of a goes to this point. Okay, let's say a, and r of b goes to this point. And with parametric curves, there is always a direction. The curve goes in this direction. Okay. Okay, but somebody else will have a different parametrization. First of all, for a parametrization, of course, we have some obvious requirements. When you are going from here to here once, you don't want the points here to go like this, come back, then go here, come back again, and then go here. Okay, so that's not a good parametrization because some points here are hit once or twice. Obviously, we don't want that. When you are moving, when your parameter is moving from A to B, you want the represented points on the curve to move like this. Okay, so you allow the speed to change. It may slow down, it may speed up, but once it passes a point, you don't want the parametrization to come back to that point again. So how do we guarantee that? Okay, we can give this long explanation. It certainly guarantees that. But how do we check it? One way to check it is to check that the speed is never zero. Okay. Actually, what we want is that the speed will never be negative. The velocity will never be negative, so that the vector will never go back. But to guarantee that, we impose that the parametrization will never stop at a point. Okay? This geometrically also has some other implication, because if the parametrization stops at that point and then starts, you can never be sure if it will continue in the same direction. It may suddenly change direction. Okay, so stopping is prohibited. Okay, so what we say is we define the velocity vector. It is almost always denoted by v. This is d, dr, r, t. Okay, sometimes we denote this by just I prime t, and sometimes in some contexts, we denote it like this. Of course, you use this notation when there is only t. Okay. Okay. So you parameterize this. You parameterize this by velocity, and now somebody else. No, you parameterize this with r, and you obtain this. But let us see what happens if somebody else parameterizes it with something else. Okay. So this time, suppose I'm using L. Okay. I start from alpha, I go to B, and I have another parameterization. So let's call it with big L. Okay, so we again want here that derivative with respect to this parameter L are L, the velocity vector. So this is different than 0. Okay, so here we also want Vt to be different than 0. Okay. Okay, so what is the consequence of having velocity vector different than 0? Every point is hit once. So this, since we already from the beginning imposed that this interval goes on to here, so this parametrization under this condition is 1-to-1 and onto. So it is invertible. Finding inverse function is always very complicated, and most branches of mathematics cherish on finding different methods of describing inverses. But theoretically, we know an inverse exists. Okay? So given a point here, we know that it comes from a unique point here, and similarly, given a point, it comes from a unique point. Okay, so now it means that suppose I'm using this inverse here. I take a point here, I go here, I use the inverse of it, it comes here. So I have a function from here to here, say phi of L. T equals phi of L. Okay, so under these conditions, this phi is invertible. And again, we have the usual assumption that this doesn't go backwards. This also takes alpha to this point. Okay, so everything as expected. So under these conditions, then phi is invertible and phi prime L is positive. Okay, because it's increasing, it's never going back. Okay, so this is the setup for parametrization. So now let's go back to arc length. So what we are doing is we have this small piece of arc. So this part is just something small here. I'm exaggerating that. Okay, so we start this point. Suppose this point and this point. I want to find the length of this thing. So if you magnify this, no matter how curled this is, if you magnify this 1,000,000 times, 2,000,000 times, it will look like a straight line. Okay? So if I join these 2 points, okay, there won't be this much difference between them. We are drawing it like this to exaggerate the situation so that we are using seconds to approximate the length. But if you magnify it, that's the whole miracle of geometry. Wherever you are, if it's a nice space, you look around, you think everything is flat. Okay, so it's only global observations that tell you that you are living on a sphere. You look around, the Earth is flat. Okay, so this is the same phenomena here. If you are on a curve, if you are sitting at a point, you think you are on a straight line. Okay, so it is reasonable to approximate it like this, but this corresponds now, let's say, to Ti plus delta T. Okay, so we divide this into small parts. So somewhere here we have A corresponding to T0. Okay, so then if this goes to B here, B corresponds, let's say, to Tn. Okay, so this part goes to this part. So this vector here is R of, okay, let me write Ti. And this vector is R of Ti plus delta T. Okay, so this vector is now that vector minus this vector. Okay, so this is R Ti plus delta T minus R Ti. Okay, so we are interested in its length. Okay, so we want its length. So we will look at Ti plus delta T minus R Ti. Okay, so in order to calculate this, we try several things. One of the cheap tricks in mathematics is you multiply something and divide by the same thing. Nothing changes, but the expression changes, and if you are lucky, the expression looks easier. So we do the same thing here. Okay, so I take R Ti plus delta T minus R Ti. I divide this by delta T and multiply it by delta T. With the setup I have here, delta T is positive. Okay, so I allowed myself to go from here to here by this one. So here delta T is a positive number. Okay, so the total length of the curve is summation of all these, summation over I. In this case, I will start from 0. If you are very, okay, let me write this n plus 1. So if it is n plus 1, then I can go up to n. Okay, so it looks uglier to write n minus 1 here. So I have all these pieces. I add up these pieces. Let me write it again. Delta T, delta T. Okay, so we have the usual expression. So it is approximately. So is approximately. Now, the nice thing about calculus is if you do this very carefully, you take the limit of this as the length of these intervals go to 0, the accumulated error goes to 0. Okay, so call it a miracle or call it a nice property of calculus used with continuous functions. Okay, so here R is continuous because it is differentiable. Okay, so in the limit, when delta T goes to 0, this sum becomes an integral, and we have integral from A to B. You see that this part is the derivative. When you take the limit as delta T goes to 0, this is the derivative. Okay, so let us remind that. Okay, I never use this color, so let me use it. Okay, so this part. So limit of this. Bu da hiç görünmüyormuş ya. Okay, so limit of this as delta T goes to 0 is velocity vector of the parametrization. Okay, so I'm also using the absolute value of this. So I have V of T dt. Okay, this T I can change. Of course, this is the dummy variable. We call it the dummy variable of integration. Sometimes we get confused that there is T here and there is T there. They are not the same T. So sometimes we write something else here. So tau is sometimes most. So let me say, just for notational convenience, this is integral from A to B, absolute value of V. Sometimes we write tau d tau. Okay, now we come to the reason why we mentioned this. Okay, you parameterize it with this, and you obtain this length. Somebody else parameterizes it with this, and it will obtain a different looking integral. Are they the same? Okay. So, of course, if they were not the same, we would not mention it. But where do I do that? Okay, so let's do it over here so that we keep seeing it. Okay, now we will calculate the same arc length using this parameterization. So next, we check the arc length formula with the other parameterization. Okay, so we have this parameterization. The other parameterization is RL. Okay, L is in alpha, beta. Okay, so note that R of T, instead of I can change R of L So which one I wrote here? T. Okay, start with a point here. Okay, this point goes to a point here, phi of L, and this point goes to, by R, to a point here, R of phi of L, okay? But that's the same thing as going with R of L, okay? So that's how we describe these things. So R of L is equal to R, so these are vectors, sometimes I forget, phi of L. We want to integrate the absolute value of the velocity vector with respect to this parameterization. Okay, so let's call it big V. Okay, so this big V is never used because at the end we'll see that whatever velocity vector you use, you'll get the same thing. But just for this thing, this L is equal to derivative with respect to L of R L. Okay, now instead of RL, I put this derivative with respect to L of R of phi of L. Okay, now we use chain rule. Chain rule, which means that I take the derivative with respect to T of R, and then, okay, so this T is described like this, but now I look it as a whole. Okay, so I take the derivative of this with respect to phi of L. Every time I see phi of L squared, I get 2 times phi of L. Okay, so that's the thing. And then, of course, I take the derivative of phi inside with respect to L. I get phi prime L. Okay, so I'm interested in writing these things. So let me see. Okay, so let's also mention that. So I have the absolute value of this is equal to, remember that this one was the usual velocity vector times phi prime L. Okay, this is a vector. I'm multiplying the vector by a number here. Okay, so now I have, this is equal to this. Now I note that somewhere I should have mentioned that this thing is positive. Phi prime is positive. Okay, so I wrote it somewhere, but I forgot. Oh, here it is. Okay, phi prime L is positive. So I have V T phi prime L comes out. Okay. So what do we have? Okay, so then I look at this thing. Integral from alpha to beta, velocity vector with respect to this person, dl, is equal to integral from, still I'm having L equals alpha to L equals beta, velocity vector t times phi prime L dl. Okay, now we change coordinates, okay, because you see that this one now, this whole thing, we remember is d phi L. So set t equals phi L. When L is alpha, t is A. When L is beta, t is B. So this integral is now, as you expect, from A to B of Vt dt. Okay, this whole thing is dt. Okay, so this assures us that it doesn't matter which parameterization you use. Choose the simplest parameterization that suits your calculations, provided that you want the derivative, you want this to be different, but this one, so let me write the summary here. So the arc length formula works for any parameterization R of t in A, B, provided that the velocity vector t is different than 0 for t in, again, another technical detail that you will be happy if the derivative is, the velocity vector is different than 0 only on the interior. At the endpoints, you allow no t behavior. This, again, comes from experience. If you were developing this theory for the first time here, you will say, well, okay, why not include everything? Okay, then we work on examples. We see that there are very nice examples. Everything works, except that at the end point, the curve has a vertical tangent. The curve is nice. It has a vertical tangent here, but algebra does not see vertical tangents. Okay, algebra says infinity, or it says this calculation cannot be done. So you have to decide whether really the calculation cannot be done or whether there's a vertical tangent there. Okay, so instead of dealing with those difficulties, we say, okay, let's keep the endpoints out, since in either case, we will be the one who's deciding what's happening at the endpoints. So the algebra is responsible only on what happens below. Okay, so the nice thing in doing algebra is once you develop the theory, once you understand what's happening, now without thinking, you just apply these things. Okay, so you are confident that it will work. Choose any parameterization. Of course, here, the components of the parameterization must be differentiable functions, the functions whose derivatives exist, so that I can talk about the velocity vector, because here you are taking the derivatives. And the velocity vector must never stop. Okay? If you have such a parameterization, you apply the arc length formula, you get the arc length of the curve. Okay? So that is what I want to say about this section. Okay, let me take 2 more minutes and then we'll have a quiz. Okay, so quiz is to write the equation of something. So while you are taking the quiz, I'll write the problem on the board so that we can remember it next time. So one last remark about arc length is the following. Okay, so if the length of the velocity vector is equal to 1 for t in, say, alpha a, b, then we say that this parameterization is parameterization with respect to arc length, is parameterization with respect to, so generally I'll write with respect to arc length. Okay, so the idea here is that if you say S equals integral from, or let me say L of t, if L of t is equal to integral, say from 0 to t of Vt okay, so let's say d tau, then the length is 1. So you are calculating this from 0 to t d tau, so it is just t. Okay, so what does it mean? If you move 1 unit from A, we are parameterizing it from A to B, this is t, and here we have our curve. Okay, and we have here our parameterization Rt. So this point goes here. And if you move 1 unit here, and then you come here, this is also 1 unit. The length of this parameterization is 1. Okay, so if you if you map all of this here, the length of this is b minus a, then this is going to be, the length of this is going to be b minus a. Okay, so that is something that we check. You see that in general, if you take the derivative of this is a function of t now. If you take the derivative of this, you obtain this. This is something positive. Okay, so it means that the length is increasing. Geometrically, it is obvious. Okay, as you move along the curve, the length you cover is increasing. Okay, but algebraically, this means that you have an invertible function. You have a one-to-one onto function. It is invertible. So even if this thing is not equal to 1, even if we are here, theoretically, you can evaluate this integral and then solve for t instead of solve for t in terms of the length, arc length. Okay, but that is only something theoretically meaningful. In practice, we cannot evaluate these integrals. We approximate this, and even if you evaluate it, you get a complicated function. It is not obvious how to find the inverse. So that's only a theoretical part. In practice, we are trying to find arc lengths. If we are into this, we try to find an arc length so that the length will be 1. Okay, so this is all we want to cover. Later on, if we find something else, we can talk.